So now we're going to look at Maxwell's equations and see how we can use them to derive the wave equation in free space. So know generally what the form of an equation, of a wave equation, looks like. You're doing a second order spatial derivative on the left hand side of the equation, so for example d2 by dx squared, and then it equals 1 over the wave speed d2 by dt squared, and you'll have whatever you're having the wave equation for, so some wave like that. And you can use Maxwell's equations to derive a wave equation for an electromagnetic wave. So to do that, we want to take Maxwell's fourth equation, and if we're in free space, this term at the bottom, this J, the current density, is 0 in free space. So M4 goes to just epsilon naught mu naught dE by dt. And the next thing we want to do is, once we know that, we can come back to it later on, but what we want to do now is do a cross product of M3. So cross product on M3 like that, which means you get the cross product of E equals the cross product of minus dB by dt, like so. If we just go to this bit to see what we're doing, so once we've done that once we do that cross product, we can use the vector identity that this section here, del cross E, is one of the key vector identities that people need to know. So del acting on del dot E minus del squared E equals del cross E. And you can then use that identity, so you've got it here, and that's equivalent to this thing, which means that's all equal to, and as this is a derivative and this doesn't depend on t, we can put the del inside the derivative. So that equals minus d del cross b by dt, and these should have underlines for vectors. There we go. Now we've got in this section del cross b, and we know that from earlier. If we zoom out again, we know that from earlier to be epsilon naught mu naught dE by dt, and we also know that del of del dot E is equal to 0. Now this is equal to 0 because you're doing del on rho divided by epsilon naught. So by doing that, you're just going to get 0 come out at the end, because rho over epsilon naught doesn't have any dependence on del, which is a spatial derivative. So now this thing here goes to 0, which means we're left with minus del squared E equals minus d by dt of this thing. So minus d by dt of epsilon naught mu naught dE by dt, like that. And then once we've got that, we're most of the way there. So then we can get rid of the minus signs. Del squared E equals d by dt epsilon naught mu naught d by dt acting on E. And then we have del squared E equals, take out the epsilon naught and mu naught, d2 by dt squared epsilon, not epsilon, E. And this is the form of the wave equation, because if you remember from the start, we had d2 by dx squared acting on some wave function equals 1 over v squared d2 by dt squared acting on the wave function. So this del here is a spatial derivative, and this d by dt is a time derivative, and that means that epsilon naught mu naught equals 1 over v squared. So it's quite impressive as well, just using Maxwell's equations, and you can find out what the speed that an electromagnetic wave propagates. And if you know what the constants epsilon naught and mu naught are, then you can see that the speed of light, or the speed that an electromagnetic wave propagates, is 1 over root epsilon naught mu naught, which will give a value, if you plug the numbers in, of 3 times 10 to the 8 meters per second.